All right, let's get into concentrations and solutions and how they're used. Some of these you already know. Molarity, mole fraction, and mole percent were very early in the year, not used all too often, but do come up on occasion. Molality is new. We can see the difference is instead of liters, it's kilograms. There's good reason why, but a different type of concentration. And then things that were parts by mass, so either by percent, parts per million, or parts per billion, which if you ever look at any kind of pollution, that's usually what the values are. It's the mass of the solute over the mass of the whole solution. So keep that in mind, solute over solution, because that plays a big role. So being able to convert back and forth and compare them is your main concept you want to get from this. There's a lot of good practice in Pearson that I've assigned, but I just wanted to kind of go through an example of a multiple choice question that could come up on your final to help you see that there's a lot of differences that are involved here. So which of these would have the highest amount of moles of chloride ion in solution? You have a mass of a molality, take note that it's a lowercase m, that's italicized, so it's a little slant. You've got a volume of a molarity, a mass of a parts per million solution, and then grams of a solid substance. So let's take a look at what that would do and how we can compare these things equally. So I'm going to start off with the one I consider easiest to follow, and that would be my 75 grams of my tungsten 4 chloride. I'm going to ignore just putting that stuff there. So I have that present. My molar mass, 325.64 grams in 1 mole of the substance. And kind of my mole ratio is that for every 1 mole of the substance, I would have 4 moles of the chloride ion. Now I'm going to ignore any kind of KSP and how much it dissolves. I would just say that it would dissolve fully, and you could also say that it doesn't need to dissolve in order to get that as a possible answer. So doing that little bit of math, times 4, and I get roughly 0.921 moles. So that's the simplest. Next, let's look at our molality. That's the first one, right? So 1.75 kilograms of this substance. And I can use molality just like molarity. Remember, it's 1 kilogram for 0.21 moles. And I can see for every 1 mole of the substance, I get 1 mole of the chlorine. So again, multiplying that out, 1.75 times 0.21, I can see that I get 0.3675 moles of chloride ion. So far, that one's not good, so I'll just cross it off and continue on with the next one. So if I'm looking at my molarity, B, 0.75 liters. My molarity, 0.21 moles for every 1 liter. And for every 1 mole of my barium chloride, I get 2 moles of my chloride ion. So in multiplying that out, I get 0.158 moles of chlorine. So that's even worse. So that one's gone. Next, I need to compare my parts per million value. So this one you want to look at kind of in a, what's it called, proportions kind of idea. So for every 210 for every 1 of these, times 10 to the 6th is my parts per million. So in order to make it easy to compare that, again, this is my solution, the mass of my solution, I want to know how many kilograms of my solvent, my solute, are present if I had 175 kilograms. So I want to make these also kilograms in order for it to be making sense to determine all my units to be the same here, right? And this is just a multiplication factor to make it a billion. So if I solve just for the amount of kilograms, what I'm going to end up getting, and this is kilograms of the solute, is 0.36, let's go 0.03675 kilograms, which translates into 36.75 grams. And so then from here, I'm going to go grams to moles, in which I've got 137.33 grams for every 1 mole of my aluminum chloride. And of course, 1 mole of aluminum chloride is 3 moles. 3 moles of chloride ions. So that ends up giving me 0.827 moles of chloride ion. And again, so that makes my best answer the first one I checked, but you can't really just do it by, that one seems good, and move on. All right, so each of these are trying to relate different parts of chloride ions, different substances. So being able to manipulate back and forth would be something that you need to be confident with in going forward. So make sure you get some practice so you're comfortable doing that on any assessment. Next, we have what's called colligative properties and how they're used. So sometimes they depend upon the number of particles when we're talking about vapor pressure. The more particles create more attractions possible. Also consider if the number of particles dissolved are equal, things that have a higher charge would have more attractions. So things that are electrolytes, which are ionic compounds or acids, have multiple ions when dissolving. So you might have 1 mole of aluminum chloride, but that's 4 moles of ions. Those are 4 largely attracted particles. Covalent compounds, like a lot of covalent gases, are generally the same amount because they don't ionize, they don't do anything in water. So the idea is that it's basically a one-to-one connection there. So keep in mind that if you have something like NaCl dissolves, that's 2 moles of 1+ charges, compared to something like aluminum nitride dissolving, that's 2 moles of 3+ charges. All right, so as long as you have equal amounts of ions, you want to look next at the charges to think about how will that affect the vapor pressure. So vapor pressure gets lowered by adding substances to it. What that means is that you get less volatile substances, things that won't evaporate as easily, won't vaporize as easily, essentially will not go into a gas form very easily. So all of this is connected to intermolecular forces. All substances will have a lower vapor pressure with stuff in it. So pure substance is going to have its equilibrium vapor pressure, while when you add stuff to it, the intermolecular forces are going to be higher. So if they're going to be higher, what this does is the equilibrium between vaporizing and condensing gets disrupted. Vaporizing goes down, right? You get less vaporizing, but the condensation is still happening until they become equal. What that does is it results in less amount of vapor and more concentration in the solution that's down as a liquid. So this will lower the amount of vapor pressure present. I'm not going to have you do the calculations. I want you to understand this part conceptually going forward. But again, the more attractive forces are going to be keeping that vapor pressure down as well. Now, one way to model this is with changing the freezing and boiling points in what's called freezing point depression, I should say, not deprivation, depression, meaning lowering, and boiling point elevation, or raising. So a normal phase diagram would show it in the black part here, but that's for a pure substance. When we add stuff to it, it expands out the liquid form, therefore lowering the freezing point and elevating the boiling point. Freezing is affected because solute particles help the arrangement of the solid solvent, so less energy is needed in the system to solidify the solution. Essentially, it makes it more dense, allows it to solidify easier. Boiling makes it higher because the increased attractions needs more energy to overcome those increased attractions, so the temperature needed to be higher. The rates at which these do these are not equal. So even though it might seem equal on here, this is just a representation of a generic form, and they can be different, but again, we don't need to focus much on that being said. Calculating these is looking at a very simple equation. We have molality, not molarity, and we have a constant of the freezing point to see the change in temperature of the freezing point. And remember, it's always going to go down. Remember, we need molality, not molarity, and you could be given any number of these values to convert, or be even given molarity to convert, and be able to get it to where you need to find any of these other values, including the constant. You might be able to need to determine the mass of the solute in order to lower a certain value. Be comfortable in finding any of the variables, including final temperature. Everything else will be given. So it's essentially a math problem determining what that final relationship is for that one unknown variable. When it comes to boiling point elevation, same relationship. Molality, you've got a constant for boiling, change in temperature for boiling, and remember it always goes up. Again, you might need to determine the mass, any of these other ones. Kb is often much lower than Kf, but not always. So we can't really take a relationship between those two concepts. This is more of determining either of them. So feel comfortable determining either of them given a sample situation where you might need to find final temperature, the molality, the mass. You generally are not going to need to find the mass of the solution, the kg part, because that would be kind of just weird. But definitely could also find the constant for this boiling point elevation. Work on the practice. Let me know what questions you have. See you soon.